Everyone, let's start our tutorial of today. We will, as we discussed before, have 2 points to discuss, which are first one extreme of functions of several variables, and the second one is Lagrange multiplier. Let's make like small summary for what we will use today. First point, which is Extrema values of function of several variables we will use the second derivative test. We will only use second derivative test. Only use second derivative test like what we have for math 103 in semester 1. But this method is applied only for function of two variables only. I mean, if you have function of three variables, we have to make it only in two variables. I mean, f of x and y only. To summarize what we will use, let's make steps of solution for this technique. First of all, you have to find, first of all, find fx, which is first order derivative for the function with respect to x, and fy and fxx and fyy and fxy. Second step will be to put fx equal to 0 and fy equal to 0 in order to get the critical points. Third step is to evaluate or find the value of d, which we call it discriminant. The point d will be equal fxx times fyy minus fxy all squared, and we will make this value, or to find this d, for all critical points we got in step number 2. And now, what are the cases for this value of d? Step number 4, you have to check the cases of d. For sure, d is a number, so it will have three values. First of all, if d bigger than 0, then you have to look for fxx at this point, and if fxx is less than 0, then at this point f of x and y has a local maximum, the opposite of the direction of this symbol. And if fxx is greater than 0, then the function has a local minimum. Second case, if d is less than 0, we said that the function has a saddle point, which is neither maximum nor minimum. We call it saddle point. And if this d equal to 0, then no conclusion about this point, and we said that test fails to define or decide what is type of this point. Is it local maximum or local minimum or saddle point? From your lecture, small note before start solving the problems, small note, D is called, like we said before, called discriminant or Hessian. And it can be found from this determinant, which is D equals determinant 2 by 2, which includes fxx, here fxy, here fxy, here fyy. And if you expand this determinant, you will get what we taught before, which is fxx fyy minus fxy all squared. And now let's go to problems, but please keep in mind that this technique does not include any constraint. No constraint will be given. Now let's go to problem number 5. States find the local maximum and minimum values and saddle points of the function. We will start with problem number B. F of x and y equal x e power negative 2x squared minus 2y squared. We should follow these steps in order to find the maximum and the minimum value. First of all, we will get fx, which is equals to, which is product rule, since we have term in x and the other one in function of x also. So the derivative of the first one, which is 1, times the second one remains a constant, plus the first term remains a constant times derivative of the second term, which is exponential. It will be e power negative 2x squared minus 2y squared times derivative of the power, which will be negative 4x. And if we can simplify this form by taking e power negative 2x squared minus 2y squared as a common factor, here we only have 1, so it will be 1 minus, in the second term we have 4x or negative 4x times x, so it will be 4x squared. Second, we can get fy, which will be x constant and e power negative 2x squared minus 2y squared times derivative power, which is negative 4y, which can be simplified to be negative 4xy times e power negative 2x squared minus 2y squared. Third, we have to get fxx. Here, as we simplified it, we have also product rule. So, derivative of the first term, which will be negative 4x times e power negative 2x squared minus 2y squared, and second term remains constant, plus the first term remains constant, e power negative 2x squared minus 2y squared, times derivative of the second term, which is negative 8x. And then fyy, which will be product rule, since we have first term includes y and second term also. Then derivative of the first, which will be negative 4x, and second term remains constant, e power negative 2x squared minus 2y squared, minus the first term remains constant, 4xy with negative sign, derivative of the second, which will be e power negative 2x squared minus 2y squared times derivative power with respect to y, take care of this, which will be negative 4y. And then at the end we have to get fxy. fxy, we will differentiate this function, first line, with respect to only y. So the first term, which is 1 minus 4x squared, is a constant as it is. Derivative of the exponential function will be e power negative 2x squared minus 2y squared times negative 4y. Then we have to go to step number 2, which is to put fx and fy equal to 0, where fx, here fx, and here fy, and then fx equals 0, which means e power negative 2x squared minus 2y squared times 1 minus 4x squared equal to 0. When you have product of two terms equal to 0, then either the first one equal to 0 or the second one. And as you know, that e power negative 2x squared minus 2y squared will not be equal 0 at all. Then 1 minus 4x squared equal to 0. This leads to that x 4x squared equals 1 leads to x squared equals 1 over 4. Then x equal positive or negative half. Then in the same step we have to put fy equal to 0, where fy in this green cloud, we have negative 4xy e power negative 2x squared minus 2y squared to be 0. Here also the same case, so we have that negative 4xy equal to 0. This means that xy equals 0, and using these values to get the corresponding y values at x equals half, y equals 0, and at x equals negative half, it does not matter at all. y also equals 0, and then as you see that the critical points are half and 0, and second one which is negative half and 0. Now you have to find the d value since d equals fxx fyy minus fxy all squared. We can summarize what we got in a table like this. We wrote here the critical point, and here the value of d for different critical points, and here fxx value, and then what is the conclusion about this point, and finally value of the function at this point, either it is maximum or minimum or saddle point. First of all, half and 0, you have to substitute in fxx and fyy and fxy, these to get the d values for each point, and then at the first point d will be 2.95, which is positive, and at this point fxx will be negative 2.43, which is negative. And if you remember that when d is positive and fxx is negative, then this point is a local maximum, and the value of the function will be half e power negative half. We substitute with half and 0 at the function at the beginning of the problem, and then the second point, which is negative half and 0. At this point d will be also 2.95, which is bigger than 0, and fxx will be positive 2.43, which is bigger than 0. And if d positive and fxx is bigger than 0 positive also, then this point can be considered as local minimum, and the value of the function at this point will be negative half e power negative half also. And now problem number C. In the same problem number 5, we have to follow the same steps like in the previous problem. We will get fx, which will be 3x squared minus 12y, and fy, which will be negative 12x plus 24y, then fxx, which will be 6x, and fyy, which will be 24, and then fxy will be negative 12. Second step is to put fx equals 0. So now let fx equal to 0, then 3x squared minus 12y equal to 0. If we divided both sides by 3, then we will get that x squared equals 4y. So y equals to x squared over 4. And now for fy equal to 0, then we have 12x plus 24y equal to 0. If we divide it by negative or by 12, we will get negative x plus 2y equals 0. And from this equation, plugging it here, then negative x plus 2 times x squared over 4 will be equal to 0. We have to solve this equation. If we take x as a common factor, we will have negative 1 plus half x equal to 0. So we have product of two terms, both are equal to 0, then either the first or the second will be equal to 0, and then x equal to 0, and in this equation we will get that y also equal to 0. Second one, x will be equals 2 after simplification, and then y will be equals to 1. So the critical points are 0 and 0 and 2 and 1. And since we know that D equals fxx fyy minus fxy all squared, we'll make our table in order to summarize what we got. Here is the critical point, and here is the D value, here fxx, and here the conclusion, and here is the type. Critical point, the D value, here fxx, and here the conclusion, and here the value of the function at this point. We will start with the first one, which is 0 and 0. And if you take a look about the values, fxx will be 6x, fyy, which is 24, and fxx always negative, which will be negative 12. At the first point, d will be negative 12, which is less than 0, and fxx, no need to evaluate it since f of xx, since the d value is negative, then there is no need to find fxx. Directly, this point is a saddle point. And the value of the function at this point will be equal to 0. And then for the second point, which is 2 and 1, the d value will be 432, which is positive, and fxx will be 12, which is also positive, and then this value will be local minimum as it is bigger than 0, and the value of function will be negative 8. And that's all for this problem. And now we move to problem number E. We have f of x or y equals sine x sine y, and we have a certain domain for the x, which is between negative y and y. Also, the y value lies at the same domain. First of all, we will follow the same steps like before. We will get fx, which will be cosine x sine y, and then fxx, which will be negative sine x sine y, and then fy, which is sine x cosine y, and then fyy, which is negative sine x sine y, sine x sine y, and we will get fxy, which is cosine x cosine y, cosine x cosine y. And now for the second step, we will put fx equal to 0. Let fx to be 0, and then we have that cosine x times sine y equal to 0. Then we have two cases. First of all, if sine y equal to 0, sine y equal to 0, if we make shift to sine y, then you will get that y equal to 0. And if you take cosine x to be 0, from the curve of the cosine, you should know that cosine equals to 0 at x equals pi over 2 or negative pi over 2, specifically these points, as we have a constraint or a certain domain for this function to be solved. And then for fy to be 0, which means that sine x cosine y to be 0, and we have to test what we got from the first equation for these cases. For example, at y equal to 0, then cosine y will be 1, then sine x equal to 0, and this occurs only in the interval at x equal to 0, and at x equals pi over 2, it occurs only if cosine y to be 0, since we know that sine 90 will be 1, so cosine y equal to 0, then y equal to positive or negative pi over 2. Pi over 2. And finally at x equals negative pi over 2, it will be negative cosine y equal to 0, which exactly is the same like before, which is cosine y equal to 0, and at this point you get that y equal positive or negative pi over 2. Then the critical points are, first of all, we wrote this one, which is 0 and 0, 0 and 0, and pi over 2 and positive or negative pi over 2. Then pi over 2 and pi over 2 and pi over 2 and negative pi over 2, and at the last line x equal negative pi over 2, at which y equal positive or negative pi over 2. We have also here two another points, which are negative pi over 2 and pi over 2, and finally negative pi over 2 and negative pi over 2. These are all what we got till now, which are the critical points. So we have to test them using, we know that d equals fxx fyy minus fxy all squared. It's better to make a table like what we did before. Critical points, the d-value, and fxx, and conclusion and the value of the function. Here, critical point, here the d-value, here fxx, and here the conclusion or the type of the point, and here the value of this function. First of all, add 0 and 0. If you substitute in d, you will get that d will be negative 1, which is less than 0. Then no need to evaluate this. It will be a saddle point. And the value function will be 0. At the second point, which is negative pi over 2 and pi over 2, it's only direct substitution. It will be 1, which is bigger than 0, so you have to evaluate fxx, which is also will be 1, which is bigger than 0, so the function has a local minimum. And the value of the function is 1. We will repeat this for the other points, which is negative pi over 2, negative pi over 2, and negative pi over 2. It will be also 1, which is bigger than 0, and fx will be negative 1, which is less than 0, so it is a local maximum, like we did before, and the value of the function will be also 1. And here, so this value will be negative 1, sorry. If we substitute with x and y, x is negative y over 2 in the basic function, it will be negative 1 times 1, and then local maximum. We will continue for the rest of the points. Pi over 2 and pi over 2, the d value will be 1, which is bigger than 0, and the fxx, which is negative, which is less than 0, so it is also a local maximum with the value of 1 also. And the last point, which is pi over 2 and negative pi over 2, the d at this point will be 1, which is bigger than 0, and the discriminant, and fxx will be 1, which is bigger than 0, so the function has a local minimum with the value of negative 1. Now we got the whole table of our problem to get the conclusion about each critical point we got in the previous steps. In order to find the value of the function at this point, and that's all. Now we move on problem number 6. It states that show that f and x and y, which is equal x squared plus 4y squared minus 4xy plus 2, has an infinite number of critical points, and that the discriminant d equal to 0 at each one of them. Then show that f has a local and absolute minimum at each critical point. First of all, we will work like before. We have to get fx, which is 2x minus 4y, and then fxx, which is 2 fy equal to 8y minus 4x, and then fyy, which is equal to 8, and then we got fxy, which is equals to negative 4. As you see here, fxx and fyy and fxy, all of them are values. Then we work like before, put or let fx equal to 0, which means 2x minus 4y equal to 0. If we divide both equations by 2, we will get that x minus 2y equal to 0. We can call it equation number 1. Again, fy equal to 0, then 8y minus 4x equal to 0. If we divide it by negative 4, we will get that x minus 2y, which equal to 0. Surprise, it is not an equation 2. We have two equations. It's exactly one equation in two unknowns. And if you remember from math 2, if you have one equation knowns, at this case you have infinite number of solution. So this equation represents infinite number of points. And for example, if x equals x naught, then y equals half x, which is equal to half x naught. Then all critical points are in the form x naught, which is the x value, and half x naught, which is the y value, which are, like we did before, which are infinite number of points. Till now we proved the first part of the problem, and we have to determine the discriminant d, which is equals fxx fyy minus fxy all squared, fxx, which is 2, fyy, which is 8, minus fxy, which is negative 4 all squared. Then it will be 16 minus 16 equal to 0. Then we derived this one. What else? Then show that f has a local and absolute minimum at each critical point. Return back to the form of the function. We have f of x and y, which is x squared minus 4xy plus 4y squared, 4y squared plus 2. If you can imagine the first three terms, we can make like completing square for these three terms. It will give us x minus 2y all squared plus 2, which is always bigger than or equal to 2 for all x and y, since it is a squared number plus 2. So therefore f of x and y is at least 2. The minimum value is 2, and then we need to evaluate the value of the function at the critical points, then f of x node and y node, which is f of x node and half x node, will be x node minus 2 times half x node all squared plus 2. This will cancel this and it will be equal to 2. Therefore, like we said before, f has its absolute or local minimum with value of 2 for all critical points in this problem. Problem number 8 states that it's an application problem. The base of an aquarium with given volume V is made of slate and the sides are made of glass. If slate costs 5 times as much per unit area as glass, find the dimensions of the aquarium that minimize the cost of the materials. First of all, the important information in this problem that the base is made of slate and the sides are made of glass. And also, the slate costs 5 times as much as the glass. And if you imagine with me this aquarium, the dimension, we imagine it as a rectangular box like this. Let the dimensions to be x, y, and the height is z. What is stated is that the base of this aquarium is made of slate and the sides is made of this side is made of glass. First of all, let's assume the dimensions like we wrote it here. Let x, y, and z be the dimensions of this aquarium, and let the cost of glass per unit area, per, for example, meter squared, will be K, and then cost of slate per meter squared or per unit area squared will be 5K, as it is stated here. 5 times as much of the glass. Then the cost of the base. In order to get the cost, we have to multiply the area of this face, which is the base, times its cost. And we know that the base is made of slate. So to multiply this area by 5K, so it will be 5K xy. And the cost of sides, if you imagine with me, we have two opposite faces, we can do it. This red faces have the same area and the same cost of material, and these faces have the same cost and area. And then the area of these faces, it will be 2xz for the two faces plus 2yz for the other two faces, and we will multiply this cost by k, which is made of glass. Then the total cost, which is function of x, y, and z, will be the addition of both costs. So it will be 5kxy plus k times 2xz plus 2yz. And the other information that we have here is that the volume, and you know that V, which is equal to x, y, and z. So the volume equal x multiply y multiply by z, and the cost, which is the function to be optimized. Then this function, which is the cost, is the function to be optimized. And from this equation, we have to use it also. Why? Since the function we have to optimize is function of three variables, and as we stated that the second derivative test for the function of several variables is only used for function of two variables only. Then from this equation we can get z in terms of x and y, then z equals to v over xy, and then we have to plug in it in this function in order to get a function of only two variables, not three. And then c of x and y only, c of x and y, it will be 5kxy plus k multiplied by 2x times z, which is v over xy, plus 2 times y times z, which is v over xy. After simplification, we can cancel this x with this and this y with this, and take 2v as a common factor. We will get that equals to the cost function 5kxy plus 2kv open bracket 1 over x plus 1 over y. And now this is the simplest form that we will use in order to get its minimum cost. So like before exactly, we have to get cx, which will be 5ky minus 2kv over x squared, and cy, which nearly the same, will be 5kx minus 2kv over y squared, and then cxx, which will be equal 4kv over x cubed, and cyy, which will equal to 4kv over y cubed, from which we can get cxy, which will be also 5k only. If you differentiate this function with respect to y, this constant, and this will be 5k only. And then like before, we can put cx, or put cx equal to 0, and then which means 5ky equals 2k times v over x squared. We can divide both sides by k, and then we can get that y equals to 2 over 5 v over x squared, and we can call it equation number 1 in order to use it. Equation number 1. Again, cy equal to 0, which means that 5kx equals 2kv over y squared. Also, we can cancel k with k. Then we will get that x equals to 2 over 5v over y squared. And this is equation number 2. And then we will plug equation number 2 into equation number 1. Then 2 in equation number 1, what we will get? We will get that y equals 2 over 5 times v over x squared, which is have this value, which is 2 over 5 all squared times v squared over y power 4. We can cancel this v with this square and this 2 with this power, and this will lead us to that y equals 5 over 2v y power 4, and we can divide it by y. Since we already know that y can't be equal 0, it's the dimension of the equation, then y cubed equals 2v over 5 by making cross multiplication. Then y equal the cubic root of 2 over 5v, and this is the first part of the coordinate of the critical point. We can plug in it again in equation number 2 in order to get the x value. Then in 2, in order to use it again, we will get after simplification that x equals 2 cubic root 2 over 5v, which is the same value, and then we will get the z value, and we know that z equals v over x and y, and then we have x and y now. Then z will be v over x times y, which is cubic root 2 over 5v, all of this squared. It will be v power 1/3 times 5 over 2 power 2 over 3. Then the critical point is cubic root 2v over 5 and cubic root, let's write it again, the critical point is cubic root 2v over 5 and cubic root 2v over 5 and v power 1/3 5 over 2 power 2 over 3. And now, since we have only one critical point, like before we talk in math 1, if you have only one critical point, so you can consider it the target of the function. So this point satisfies the equation and give you the minimum cost. But to check this, we will make the discriminant only to check. We don't need to make it, but we make it to satisfy the conditions like before. To check, we know that D equals Cxx Cyy minus Cxy all squared. We will use the value of x and the value of y in order to evaluate this discriminant. Then at x and y, which is cubic root 2v over 5 and cubic root 2v over 5, the discriminant d will be 75k squared after simplification, which is bigger than 0. And we have that Cxx will be 10k, which is also positive. And then C of x and y has a local minimum. Then the dimensions that satisfy or that minimize the cost are these dimensions. We can highlight it. These dimensions makes the cost minimum as we can. And now we go to the second point of today's tutorial, which is Lagrange multiplier. Again, we use this method in case we have a constraint or in case of a constraint is given to find the extreme values of f of x and y and z subject to the constraint g of x, y, and z equals k. We have to follow the following steps of solution. We have to find the all values of x, y, and z and the new parameter lambda, which is constant. That's why we call it Lagrange multiplier, such that nabla f equal lambda nabla g according to the constraint g of x, y, and z equals k. This exactly equivalent to equate each component of this vector, the vector nabla f and the vector nabla g, by each component. For example, fx equal lambda gx and fy equal lambda gy and fz equal lambda gz according to the constraint g of x, y, and z. The main target or the main aim is to solve or to deal with these four equations in order to get x, y, and z and lambda clearly, and then go to step number 2, which is to find f of x, y, and z for all points you get from step number 1, and the largest value will be absolute maximum value and the smallest value will be absolute minimum value. And now we will go to solving problems about this. Problem number 11, find the maximum and the minimum of the function f of x, y, and z equals x minus 2y plus 5z on the sphere x squared plus y squared plus z squared equals 30. And here you can clearly see that this equation was equal to number which is the constraint equation, and this function to be optimized. And since also we have a constraint equation and we have also a function of 3 variables, we have to use Lagrange multipliers. Then we will solve it using Lagrange multiplier like what we explained. First of all, apply Lagrange multiplier. In order to find the maximum value of f of x and y subject to the function, which is this function, the constraint function. How? We have to start from nabla f equal lambda nabla g according to the function g of x, y, and z equals k, which exactly equivalent to, like we stated before, fx equal lambda gx, fy equal lambda gy, and fz equal lambda gz according to the function g of x, y, and z equals to k. And this will follow us to fx, which is 1. Here is f of x, y, and z. Fx, which is 1, equals here g of x, y, and z equals x squared plus y squared plus z squared equals 30, which is k. So gx will be 2x times lambda. It will be 2 lambda x. And the second one, fy equal lambda gy, fy will be negative 2 equal to lambda y, which is lambda gy. And third one will be derivative with respect to z, which is 5, equals to 2 lambda z, according to the constraint equation, which is x squared plus y squared plus z squared equals 30. From this equation, you can find that x equals 1 over 2 lambda. And from this one, you can get that y equals negative 1 over lambda. And from this one, you can get that z equals 5 over 2 lambda. We can write it again. 5 over 2 lambda. And according to the constraint equation, we can call it equation number 4. And we can use these values we got for x, y, and z to plug in it in equation number 4 in order to find the value for lambda, like this. So in equation number 4, we will get that x squared, which is 1 over 2 lambda all squared, plus y squared, which is negative 1 over lambda all squared, plus z squared, which is 5 over 2 lambda all squared, equal to 30. Simplifying this, it will be 1 over 4 lambda squared plus 1 over lambda squared plus 25 over 4 lambda squared equals 30. We will get that lambda squared equals 1 over 4, then lambda equal positive or negative half. And then we have to use this lambda in order to find the values of x, y, and z for each lambda using lambda values, which we have two values, then we will have 2 points for x, y, and z. We will get the following points, which are 1, -2 and 5 and -1, 2 and -5. Then we are done with finding the critical points. Then we have to substitute with these critical points in order to find the largest and the minimum and the minimist, or the largest and the smallest value of this function. Then f of 1 and -2 and 5, we will use the function itself in order to find the value at each critical point. At each critical point, f of x, y, and z for this point will be 30, and f at the second point, which is 1, -1, and 2 and -5, it will be -30. Then this is the highest value. We can consider it absolute maximum value or maximum value, and this is the smallest value. We can consider it absolute minimum value, and we can consider it the minimum value of this problem. Problem number 13. A space probe in the shape of an ellipsoid of equation 4x squared plus y squared plus 4z squared equals 16 enters Earth's atmosphere and its surface begins to heat. After 1 hour, the temperature at the point x, y, and z on the probe surface is t of x, y, and z, which is function of 3 variables. Find the hottest point. Find the hottest point of or on the probe, the hottest point on the probe surface. Here we have to find the hottest point, which means that we have to find a location or coordinates for x, y, and z on this function, which is t capital of x, y, and z. And here also, since we have a constraint equation, which is this one, and function of several variables and exactly 3 variables, so we have to use Lagrange multiplier method, which states that when you have t of x, y, and z, which is 8x squared plus 4yz minus 16z plus 600, subject to the constraint equation, which is g of x, y, and z, which is equal 4x squared plus y squared plus 4z squared equal to 16. We have to apply Lagrange multipliers method, which is nabla t equal lambda nabla g, according to g of x, y, and z equals to k. And this equivalently can be written as tx equals lambda gx and ty equals lambda gy and tz equals lambda gz according to g of x, y, and z equals to k. وده يا جماعه كده الشكل العام بتاع البروبلم بتاعتنا اللي احنا عايزين نعمل لها ايه؟ نعمل لها سولفنج دلوقتي. طيب نعمل الكلام ده كده بقى نطبقه عشان نجيب الايه الفاليوز بتاعتنا. تعال نجيب تي اكس وجي اكس وتي واي وجي واي اند سو اون. طيب تي اكس هتكون 16 x equals lambda gx. It will be 8 lambda x, and we can call it equation number 1. Second equation ty, we will differentiate the function t with respect to y. It will be 4z equals lambda gy, which will be equal to lambda y, and we can call it equation number 2. And then the third one, it will be 4y minus 16 equals 8 lambda z. We call it equation number 3. This happens according to the condition, which is 4x squared plus y squared plus 4z squared equals 16, and we can call it equation number 4. وزي ما قلنا يا جماعه قبل كده ان اللعبه كلها هتكون في ايه؟ انك how to solve this system of equations in order to find x, y, z and lambda. طبعا لو انت خدت بالك هنا هتلاقي ايه؟ هتلاقي ان احنا ممكن نركز كده في equation number 1. equation number 1 هتلاقي الايكويشن دي هي الوحيده اللي في only two variables x and lambda. equation number 2 z lambda y, equation number 3 y z lambda, equation number 4 x y z. يبقى اقدر اقول لك دلوقتي اهو، انت شفت معايا دلوقتي ان الايكويشن ديت first equation is the only equation that includes only two variables which are x and lambda. يبقى اقدر اقول لك كده اهو from equation number 1 اقدر اقول ايه؟ ان انا ممكن اخد ال 8x common factor، هيبقى لي ايه؟ هيبقى لي 2 minus lambda equal to 0. وزي ما قلنا قبل كده if you have two blocks multiplied each other will be equal to 0. This means that the first one equal to 0 or the second one equal to 0. ودلوقتي انا وصلت ليه يا جماعه؟ وصلت ان انا معايا اتنين values اهم، x equal 0 and lambda equals 2. يبقى انت محتاج تكمل البروبلم انك تجيب لي y و z ولامدا لكل كيس. يعني انت محتاج تعمل ايه؟ عند اول كيس ديت لازم تجيب y و z ولامدا، وعند تاني كيس لازم تجيب لي x و y و z كليرلي عند كل كيس من دول. تعال نبدا بكيس واحده منهم. if lambda equals 2، لو انا بصيت يا جماعه على ايكويشن نمبر 2 حطيت هنا فيها اللامدا ايكوالز 2 اهو، عشان اوضحها لك برضه اقول لك اهو ان ايكويشن نمبر 2 عشان لما تيجي تذاكر تبقى شايف الكلام كويس اهو. ان ايكويشن نمبر 2 هقدر اقول ايه دلوقتي؟ اقدر اقول ان 4z equals 4y which implies that y equal to z. حط دي بقى معاك في دماغك عشان دي مهمه جدا الحته دي. طيب سنس ان احنا قلنا من الاول ان الايكويشن الثيرد ايكويشن دي مالها يا جماعه؟ فيها برضه لامدا وواي وزد بس، فهعمل ايه؟ هاخد الكونكلوجن ده كده واحطها فين؟ واحطها في ايكويشن نمبر 3. يقول له كده ان ايكويشن نمبر 3. فاقدر اقول لك ايه؟ اقدر اقول ان 4y minus 16 will be equal 8 times 2 times y. 8 times 2 times y دي منها ممكن اقول انها دلوقتي عندي 16y minus 4 it will be 12y equal negative 16. ومنها اقدر اقول ان y equals to negative 4 over 3. وبنفس الطريقه تكون هي مين يا جماعه؟ هي z زي ما احنا قلنا. كانت عملت ايه؟ انا كان معايا يا جماعه اللامدا ايكوالز 2، جبت واي وجبت الزد، فاضل اعمل ايه؟ اجيب اكس. الايكويشن الوحيده دلوقتي اللي فيها اكس هي ايكويشن نمبر 4، فهعمل ايه؟ هقول لك كده ان ايكويشن نمبر 4 اهو. ان ايكويشن نمبر 4 معاك دلوقتي لامدا وواي وزد، فممكن اجيب منها الاكس، فاقدر اقول ان 4 اكس سكويرد بلس واي سكويرد اللي هي نيجاتيف 4 اوفر 3 سكويرد بلس 4 في زد سكويرد اللي هي نفس الواي 4 اوفر 3 سكويرد ايكوال 16. شفت سولف الكلام ده كله هقدر اوصل لايه؟ هوصل ان اكس هتكون ايكوال بوزيتيف اور نيجاتيف 4 اوفر 3. كده يا جماعه خلصت اول كيس اهو. يبقى اقدر اقول therefore the critical points are، نكتبهم مع بعض كده. عندك الاكس اهي بوزيتيف ونيجاتيف 4 اوفر 3 والواي والزد كونستانت، فهعمل ايه؟ هتبقى 4 اوفر 3 and negative 4 over 3 and negative 4 over 3. دي كده أول critical point، والcritical point الثانية هتبقى negative 4 over 3 ونيجاتيف 4 over 3 and negative 4 over 3. وكده أنا عملت إيه؟ كده أنا بس جاوبت إيه؟ كيس نمبر 1 اللي هي equals كام؟ equals 2. تعال نخش بقى دلوقتي على إيه؟ على الكيس الثانية بتاعت x equal to 0. نكتب كده مع بعض if x equal to 0. تعالى كده نحاول نجيب الايكويشن دي قدامنا عشان نبقى شايفينها. نحطهم كده قدام عينينا عشان نبقى شايفينهم بس. طيب لو x equal to 0 يا جماعة هلاقي ايه؟ هلاقي ان عندي first equation خلاص انا استخدمتها، ما عنديش بس غير ايه؟ غير السكند والثيرد equation. بس في هنا حاجة مهمة جدا، انا معايا x equal to 0 دلوقتي، فممكن اخد equation نمبر 2 احطها في equation نمبر 4، بقت equation بس في مين؟ في z ولامدا y. تعال نجرب كده، اقول لك اهو from 2 in 4 from 2 equation number 2 in equation number 4. انا معايا ايه؟ معايا من equation number 2 ان كل 4z ب 2 لامدا y. يبقى اقدر اقول لك ايه؟ اهي تبقى 0 سكويرد بلس y سكويرد بلس 4z سكويرد، فهتبقى ادي ال 4 والزد بكام؟ هتبقى هاف لامدا y all سكويرد equals to 16. ومنها ممكن اقول ايه؟ ممكن اقول ان y squared plus lambda squared y squared equals to 16. ممكن نسمي دي كده equation number 5 لان اكيد هحتاجها قدام. طيب كده انت عملت ايه؟ جبت لي equation جديده فيها مين ومين؟ فيها y ولامدا. طب ما تحاول نعمل نفس الكلام تاني بس في equation number 3. يلا هقول لك اهو from 2 in equation number 3 عشان اوصل لنفس التارجت. فاقدر اقول لك ايه؟ 4y minus 16 will be equals 8 lambda z اهي 8 الزد بكام؟ which is half lambda y. فدي تكنسل دي، هوصل في الاخر لايه؟ هوصل ان معايا 4 هنا في لامدا كمان عندنا بس هنا بره. هيبقى عندي دلوقتي ايه؟ هيبقى عندي ان 4y minus 16 equals 4 lambda squared y. يعني لو عملت divided by 4 الايكويشن دي كده هيبقى عندك ايه؟ هيبقى عندك lambda squared y equals y minus 4. وممكن اسمي الايكويشن دي كده نمبر 6. فلو انت بقى عملت بلجن ايكويشن نمبر 6 into equation number 5 هوصل لايه؟ هوصل لايكويشن بس في مين؟ في الواي، وده اللي عايز اوصل له اهو. نكمل كده مع بعض. And then from 6 in equation number 5 فيبقى عندك y squared plus y times y minus 4 equals to 16. after simplification هوصل لايه؟ هوصل ان يبقى عندك 2y squared minus 4y minus 16 equal to 0. after solving this equation هيبقى عندنا ال y equal 4 or y equals to negative 2. You can use equation number 4. You can use equation number 4 in order to find the value of the z, and then in equation number 4 you will get that z equals to 0, and again here in equation number 4 we will get that z equals positive or negative root 3, and now we got y and z and also x, and then we can find the critical point. Then the critical points are 0 and 4 and 4, 0 and the negative 2 and root 3, which is this one, and 0 and negative 2 and the negative root 3. Now we have three critical points, and previously we have found another two critical points. So we have in total 5 critical points, and then we have to evaluate the value of the function at this all 5 critical points like this, and we can summarize what we got in a table like this: the critical point and the value of the function, and here is the conclusion. The value of the function, which is 8x squared plus 4yz minus 16z plus 600, and here is the critical point itself. We first start from 4 over 3 and negative 4 over 3 and negative 4 over 3. This is the first one. Second one, negative x, negative 4 over 3 and negative 4 over 3 and negative 4 over 3. Third one will be 0 and 4 and 0. The fourth one will be 0 and negative 2 and root 3. And the last one, which is 0 and negative 2 and negative root 3. If you use this point to substitute in this function, you will get first point 642.7, and the same here 642.7, and the third one will be only 600 as x and z equals 0. The fourth one will be 558.4. The last one will be 641.6. As you see that this point and these points are the highest values. Then both of them are absolute maximum value or maximum value, and this is the lowest value, which is absolute minimum value. A fast review about this problem: the main idea is to figure out how to solve this 4 equation and 4 unknowns in order to find all critical points. And if you find the critical points, then it's simply you can substitute in the function in order to get the value of the highest value and the value of the lowest value to get the maximum and the minimum value of this function. And now problem 14, which is the last problem in this worksheet. It's also an application problem for Lagrange multiplier or maximum or minimum. Problem 14 states that find the dimensions of the closed rectangular box with maximum volume that can be inscribed in a unit sphere. دلوقتي انت عندك ايه؟ عندك يونت سفير محتاج تدخل فيها ايه؟ rectangular box. طيب تعال نترجم كده كل كلمه معناها ايه. First of all, the word unit sphere means that the equation is x squared plus y squared plus z squared equals 1, which is the radius squared. And you have to inscribe in it a rectangular box. طب if imagine with me what we need to get. We have a sphere or a ball in the XYZ plane, and we need to inscribe in it a rectangular box like this. So we can first of all assume the dimensions of the box. Let the dimensions of the box to be x, y, and z, which are here. This x and this y and the height to be z. In order to inscribe this rectangular box in the sphere, we have to be sure that, and we can inscribe this rectangular box if and only if diagonal of the box equal diameter of the sphere. Here is diagonal of the box, the green line, which is also the diameter of the sphere, and then diameter of a sphere equals 2 as r equals 1, and from Pythagoras we can state that x squared plus y squared plus z squared should be equals to 4. And this is our target, that is g of x, y, and z. And in order to inscribe this rectangular box in the sphere, we have to know its volume. So V of x, y, and z equals to x, y, z, and now we have a function to be optimized according to a certain constraint. If you remember, this 4 is d squared. And then we can apply Lagrange multiplier like before, exactly like before. We have that nabla v equal lambda nabla g according to the condition g of x, y, and z equals k, which is equivalently can be written as vx equals lambda gx and vy equals lambda gy and vz equals lambda gz according to the function g of x, y, and z to be equals k, and this can lead us to yz, which is fx equals 2 lambda x, and vy, which is xz, equals 2 lambda y, and the third one, which is xy, equals to lambda z, and the constraint equation, which is x squared plus y squared plus z squared equals 4. And this equation number 1, this equation number 2, this equation number 3. وزي ما قلنا قبل كده يا جماعه ان اللعبه هنا انك تحاول تسولف ايكويشنز مش اكتر. طيب لو انت خدت بالك هتلاقي ايه؟ first equation yz equal, second xz equal, third xy equal. طب انت لو عملت ملتبلاي الفيرست في x والسكند في y والثيرد في z هتجيب كونستانت تيرم. طب ما تيجي ننفذ الكلام ده كده مع بعض. لو عملت يا جماعه دي كده اهو، لو عملت هنا كده تايمز x هيبقى عندنا ايه؟ هيبقى عندك x y z equals 2 lambda x squared. نسميها 5. ولو عملت هنا يا جماعه times the missing variable which is y يبقى عندك برضه x y z equals 2 lambda y squared which is equation number 6. and again هنا times z هيبقى عندك ايه x y z equals 2 lambda z squared. we call it equation number 7. طبعا واضح جدا دلوقتي عندنا ان x y z x y z x y z then both are equals. هقول from equation number 5 and 6 and 7 one can see that both are equal, and we know that lambda can't be equal to 0. At this case we will get no volume if lambda equal to 0. Therefore x squared equals y squared equals z squared, and this leads us that x equals y equal to z, and for sure we neglect the negative value since x, y, and z are all dimensions. And we can plug this value in equation number 4 in order to find the critical points, which is x, y, and z value. So in equation number 4, it will be x squared plus x squared plus x squared equals 4, which means 3x squared equals 4, and x will be positive only, not positive or negative, positive only 2 over root 3, and then the critical point is 2 over root 3 and 2 over root 3 and 2 over root 3, and we have to find the volume. So V at this point 2 over root 3 and 2 over root 3 and 2 over root 3